Good morning, colleagues. My name is Michael Diop. This is Steven Salek. My partner today will be presenting the MS32. Before we get started, let's go over today's agenda to cover some of the topics we'll be going through in our presentation. Firstly, what is the MS32? We derived the name from first initials of our first names, and the 32 comes from the design being a 32-bit processor. We'll also cover pipelining. What does it do? How is it beneficial to us? How do we implement it in our design? As well as how we handled such instructions as branches, jumps, interrupts, and returns. As well as breaks. Firstly, what is the MS32? The MS32 is a 32-bit MIPS processor that utilizes a pipelined architecture. You can see here from our top level diagram that it looks very similar to the multi-stage top level. You can see here that there's data memory, I/O memory, and you can see similar modules such as the control unit, instruction unit, and the integer data path. However, there are 3 new modules we will be covering in the later slides. The reason pipelining is so advantageous is because it increases the processor's throughput, which is the total amount of work done in a period of time. This is not to be confused with the latency, which is the time it takes to fully execute a single instruction. Now, how does our processor increase the total throughput of the design? Well, control signals are generated in the decode stage, and they're passed through the whole pipeline to be used for the future registers. And this means that new instructions can be decoded every clock cycle, which also implies that new instructions or each instruction is being executed and is being completed every clock cycle too, whereas pipelining, you can see where it would decode, then it would need to take a certain amount of steps to execute and finish before the next instruction is decoded. Now, there are 3 important modules that are needed to successfully implement pipelining. The 3 listed here: forwarding unit, the branch control, and the break counter. In our design, we chose to implement these 3 separately in the top level, whereas in other pipeline architecture designs, it's possible that they could include all 3 in a single hazard control module to make it more simplistic and easier to read. However, we found it easier to implement the 3 separate ones in our top level. Firstly, we'll go into our forwarding unit, and why do we need it? What does it do? There are times in your instruction memory where the current instruction's operand register is the same as a previous instruction's destination register. And at these times, we would need to wait for the previous instruction to complete and for the destination register to receive the correct value. And waiting for that would destroy the whole point of pipelining and the whole efficiency purpose of having the throughput be increased every clock. Now, this is where forwarding comes in. Forwarding allows us to not have to wait for the previous instruction to finish before we can use it in the current instruction's operands. To paint a better picture, we decided to show you guys a diagram of our 5-stage pipeline. You can see here, this is the current instruction, and it's able to receive values from the destination register of the previous, as well as 2 instructions prior to the current instruction. Now, it's also good to note that forwarding will not occur when the destination register is R0, because we won't be able to write to R0. So we included that in our implementation. If you guys can see here, DH1RS, data hazard 1 for RS. it checks if the destination register is R0, and if it is, then we will not have a data hazard. Whereas if it wasn't, then it checks if the current RS is equal to the destination register of the instruction prior, which is why you see RDM1, which stands for -1. Now, how does our design know when forward? To illustrate a better example, we showed a simple 2-step instructions right here. Now you can see here that R3 is dependent on this adds R3 destination. So our forwarding unit detects that they are equal. You can see here. So it is, the case is that it is RS, so that way the data from, the data is forwarded through the FA mux, whereas if it was RT, it would be forwarded through the FB mux. It is also good to note that RD would be for R types, whereas RT would be the destination for I types. Now, forwarding doesn't always work, unfortunately. There are cases when we do need a stall, which is being the case of a load word, because there is an extra step to write back to the register, so we wouldn't be able to receive that data on time in order to use it in the current instruction. So this is why we would need to stall. And we implemented a stall by checking to see if the instruction is a load word. This is the signal to check if there's a read on the memory, as well as it checks it to see if the destination register of the load word is equivalent to any of the operands, RS or RT, of the following instruction. Now when that stall flag goes high, you can see that it stops the PC from incrementing through these two NOR gates, as well as it stops the IR from loading the next instruction. This way that we're able to flush the current instruction in to stall and wait that one more cycle so that the data would be ready for the next instruction. For branches, we had a branch control module. Pipelining, it creates some difficulties with branching, so we created a module to implement our branch control. So we can see here that it takes our IR and checks to see if it is one of the branch opcodes, and if it is, then it signals our is branch flag goes high, goes out here, and also takes that opcode and determines the to see if we do need a branch, which it goes into here and do branch. It's also good to note that we do have to wait one clock cycle for the instruction to finish comparing the two before it is actually used in the branch.
Can you go back there for a sec?
Yeah.
So along that line, so it's the third clock cycle, you're doing the subtract, right? The compare is kind of the subtract on the branch not equal, for example.
Yeah.
So then this signal is being generated on the third clock.
So in decode, you see the branch.
Right.
But we have to wait one extra clock cycle because the way the forward unit takes the forwarded data, it's after the pipeline, that's after the ALU. So we have to wait for that data to be clocked before we can forward, and so we had to stall. That way the data would be available. It obviously isn't as optimal as we would have wanted it to be. The ideal situation was that we were going to branch and decode, and that's it. But the problem we ran into is that the forwarded data wasn't ready yet.
But you got to do the subtract to see, like that bottom box is whether you really have to branch or not.
Right, that does check the condition. So I mean, it takes the opcode. If it's branch if equal, it'll check if the.
So you actually have a set, you don't use the ALU for that, you just use that
I
logic?
use a separate.
That's great, that's clear. Very good.
And here's just an example to illustrate how a branch would take place. So in clock 1, it sees that we do have a branch, PC stops incrementing, IR isn't loaded, and our flags, hypothetically, if they did go high, it'll show these steps right here. And if it is true, then the do branch signal loads the PC with the branch address seen here. We have a different sign extension because of pipelining, so that's why you can see that it's not really, you guys aren't really familiar with this branch address.
So tell us about it then, since we're not familiar.
Well, the pipelining, it's a little different, so that way, yeah.
So I mean, the reason it's a little bit different, and it doesn't really say there, is because the sign extension is pipelined. It's not coming directly out of the IR like our normal sign extension is. There's a pipeline register in between, and since the branch is executed 1 clock later, we needed to pipeline the sign
There you
extension.
go. Got
Because
it.
we do no op the IR, so we would no longer have a sign extended value coming out. It would just be zeros. And then the PC out, we just wanted to note over there that the PC plus 4 just represents that since we stopped incrementing the program counter once we saw the branch, the next instruction is already sitting there on PC out. We don't have to add anything to the PC or subtract anything from it.
No, that helps. Yeah, thanks.
And lastly, we have our break counter. In the multi-stage, when a break instruction is fetched, all the instructions are done. We just break and display our reg file and all of the memory contents. Whereas in a pipeline design, when we break, there's still instructions that need to be fully completed through the pipeline. That's why we have a break counter. And we implemented this by a signal, and when our count is 4, which is the 4 steps it takes to fully execute, then that's when our break stops and we dump our reg file into our memory contents.
So for jumps, we handle those in decode as well. If a jump is seen in decode, we don't increment the PC. The PC load goes high because the effective address is going to be loaded into the program counter on the next clock. And IR load goes low because we don't want the instruction that is happening next in instruction memory to be executed. And then we also clear the instruction register so that the jump isn't executed again the next clock. So in order to handle interrupts using the stack, I'm strictly going to talk about the module 14 interrupt and not the module 13 just for the sake of time. And it's a bit more interesting. So in order to do that, we needed 3 additional modules. The interrupt servicer, the return servicer, and a flag counter, and I'll be walking through each one of them. So the interrupt servicer, it activates when the interrupt signal is seen by the processor, and it's basically a custom set of instructions that are going to do the set of micro operations that we need to implement, or to get to the ISR basically. So the first one is to decrement the stack pointer. The next is to place the current program counter into memory pointed at by the stack pointer. We decrement again, we store the flags into the memory, and then we take the PC out of data memory from the location 3FC, and that's going to be the location of the ISR. So the way we implemented it, we have an array of registers, 50 bits wide, 10 deep. That just happens to be the size of our pipeline register. Not necessarily all the bits are really used. We also have a counter, and the counter is actually going to start when the interrupt's seen. I'll explain more exactly how that works, but it's going to start, and it's going to be it's going to index the array, and the output will be coming out here, and that's going to be our control. That's going to be going through the pipeline and executing the micro operations. So we have, all of these are just different comparators just for different events. Like up here we have the busy signal, like we're currently servicing the interrupt. We have the finish signal and a couple others, which I'll be walking through a waveform, so you'll be able to see what each of these signals are doing. This one down here in particular is a select for a MUX that controls what data is going into the data import on the data memory. So when count equals 3, you'll see that that we're going to load the program counter into memory. When count equals 5, we're going to load the flags into the memory. And then the normal operations of this MUX is just to let RT out go through, which is our pipeline version of our data out from our IDP.
Before you go on, could you
Sure.
go back, just explain that your 50 by 10 custom instructions?
Yeah,
What you mean by custom instructions?
Custom instructions, since the let me go back here. Since this isn't really an instruction that we have implemented in MIPS to load our flags into data.
Right.
I had to kind of change up the control signals a little bit. I'm not using the control unit to decipher those instructions. I've already just loaded some memory
Okay, yeah.
with,
It's kind of like microcode
yeah, just like.
to do those things.
Yeah.
Okay,
I don't show exactly because it's just ones and zeros that
Yeah.
would take quite some time to walk through.
that's good.
But I'll be showing you the waveform which will depict what's going on. So we can see over here that the interrupt request goes high. And on the next clock we have an SR flop that is going to basically start the counter. And this first instruction here, you don't see it depicted by the in progress signal. The reason being because the in progress signal waits for count to be higher than 0. So the count has technically started here during this clock cycle. And the first 2 instructions are actually just empty instructions, nothing's happening. We're allowing some time for what was in the pipeline registers to finish.
Yeah,
Because I had some bugs when I tried to jump straight into it.
right.
So the first instruction here is going to be decrementing the stack pointer, and you can see that that's happening here once it makes its way through the pipeline.
Mm-hmm.
Register 29 is being loaded with 3F8, which is 3FC decremented. The next instruction is going to be storing the PC, which we can see happening here. You can see PC out here is 58 when that interrupt occurred, and so we're going to be coming back to that spot. So we're writing to memory address 3F8 with the data at hex 58. The next one is to decrement once again, and we'll see that happening here. Register 29 being written to with 3F4.
Mm-hmm.
Following instruction is going to be storing the flags. So this is at hex 15, which is our 5 flags being loaded into memory at address 3F4. The final instruction is to grab the ISR location out of the memory and place it into the PC. I didn't want to fill this up with too many signals, so I'm not showing the memory read or anything, but you can see here with the PC out that once we're finished with the interrupt, that's the interrupt finish signal, that the PC out is going to have the address of that ISR.
Mm-hmm. Got it.
So our return servicer is really quite the same thing. It's just a kind of a smaller, it's one less instruction and it's slightly different. So the first micro operation is to load the flags with the flags that we saved into the memory. We're not really loading the flags here. What we're doing is placing them into kind of a temporary register to hold them until we're ready and finished with the return. And then we're going to place the flags into the flags register. Because otherwise it would just get wiped away by the clock from the flag register. And we want it to appear like nothing ever happened. Like if you were to remove the interrupt having happened, it wouldn't look like anything changed. I'll be explaining that more in detail shortly. So the stack pointer gets incremented, and then we're going to take the PC out as well. Increment the stack pointer one more time, and so that'll be back at 3FC, which is where it started before the interrupt occurred. So there's slightly different events happening, but I'll be explaining that. So one issue that arises, this is what I was talking about with the flags, is that we grab them out but we're not ready to put them back into the actual flag register. We have to wait a little bit of time before we do that. And so the problem was that the return servicer, well, when we wanted to put the flags back, the servicer was already done. And so we have a counter within the servicer, but we can't use it because it doesn't go long enough. So we needed a separate counter. There may have been a way to implement it so that we could have made the return servicer last long enough to properly put the flags back. But it was easier just to use a separate counter.
Was time ever a factor? Time is kind of creeping in on you.
So we have to wait until the resumed instruction is in the IDEX stage before we place the flags back in the register. So once we return from the interrupt, we have to wait a little bit longer for the next instruction to make its way down the pipeline to properly, for the timing to be right to put the flags back in. So this is just a little example. So say we have an add, and then that creates some flags. The interrupt occurs. We return from the interrupt. This subtract is just being fetched here. So it's not even ready to get the flags back yet. The flags should be there right before we execute the subtract.
Mm-hmm.
So we kind of wait a couple clock cycles before we put the flags back in the flags register. So it's just a counter that goes from 0 to 10 or hex A. And it says it sends a load signal when it reaches A. It starts when the return servicer starts. The return servicer is a slightly shorter counter, so that's why this is a bit longer. I just wanted to note that having the counters when we were trying to implement the interrupts was incredibly helpful because we were able to see exactly when data needed to be where. We could say, okay, when count equals 6, we can send this signal to load this register. It was quite helpful.
Mm-hmm.
So this is the hardware connection, kind of abstracted a little bit. I'm going to walk you through how an interrupt occurs. So when an interrupt signal is seen, we generate the interrupt select signal, which is actually the output of the SR flop, but this makes sense. So we set the flop. On the next clock, we'll have the interrupt servicer starting, and that signal is also brought back to the mux. It's one of the mux selects. And that's going to allow the data from the interrupt servicer, which is the custom instructions, to pass through this mux into our pipeline register. Normal operation of the processor, this is just going to be zeros, the selects, and our normal control will pass through. So yeah, you can see the interrupt select signal activating the mux and also allowing the data to pass through. When it's finished, it's going to send out a finish signal, and that's going to reset the SR flop and allow normal instructions to, or normal operation to continue. The return servicer works exactly the same way, it's just a slightly shorter amount of time. So overall, it takes about 10 clocks to enter, about exactly 10 clocks to enter the ISR from when the interrupt is seen. And like I said, that's not quite optimal, and the reason being is because there's that fluff on each end of the instruction, the custom instructions. I have those empty instructions to allow the pipelining to finish what it's doing and whatnot, and it just kept it bug-free. So it could be slightly more optimal. 7 clocks for the return from interrupts instruction. So our pipeline architecture for memory module 14 was about 3 times faster than our multi-cycle implementation. It was the exact times it took and exactly how much faster it was. So that's it. Thank you.
Any questions?
Any questions? No?
That was excellent, excellent presentation.